Somewhere in the darkness between the stars, there is a clock. It is falling, not quickly, not yet, but with a slow, inexorable grace, pulled by something it cannot see. The clock is ordinary. It ticks the way any clock ticks, 1 second following the next, in the steady rhythm that has measured human life since we first thought to measure it. You are watching from a distance, a safe distance, and at first, everything seems normal. The clock drifts, the seconds pass, the digits change. But as it draws closer to the object pulling it inward, you begin to notice something wrong. The ticking slows, not because the clock is broken, not because some mechanism inside it has failed. The clock is perfect. Time itself is bending. The digits change less often. The light coming from the clock shifts, blue fading to red, red deepening to a color your eyes can barely register. The clock is dimming. It is reddening. It is fading from the visible universe like a word being erased from a page, letter by letter. And then, at a certain distance from the object, a distance you can calculate with pen and paper using equations written over a century ago, the clock appears to stop entirely. One last digit, frozen. One last photon, stretched into silence. But here is the part that keeps physicists awake. The clock has not stopped. From its own perspective, nothing unusual has happened at all. It crossed an invisible threshold, no wall, no barrier, no flash of light, and continued falling. The seconds kept ticking, the digits kept changing. From its point of view, everything is fine. From yours, it has vanished from reality. Two observers, two completely different versions of what happened, and according to our best theory of gravity, the same theory that tells satellites where to orbit and light how to bend around galaxies, both versions are correct. This is a black hole, and that contradiction, that quiet impossibility, is only the beginning. Black holes are the most asked about objects in the universe, and for good reason. They are the places where everything we think we understand about reality reaches a wall. Not a wall built from matter or energy, but from the limits of the language physics uses to describe the world. On one side of that wall, Einstein's equations work flawlessly. On the other side, inside the event horizon of a black hole, those same equations produce answers that contain infinities, divisions by zero, quantities that no instrument could ever measure and no mind could ever pass. The theory does not crash. It simply stops making sense. And yet, black holes are not abstractions. They are not thought experiments scribbled on whiteboards in university hallways. They are out there, right now, by the billions. Every large galaxy harbors one at its center, a supermassive engine millions or billions of times the mass of the Sun. Our own Milky Way has one. It is called Sagittarius A star. It weighs about 4 million solar masses, and it sits 27,000 light-years from where you are listening to this, quietly bending starlight and swallowing anything that ventures too close. In April of 2019, humanity saw one for the first time. The Event Horizon Telescope, a network of radio dishes spanning the entire planet, linked together to form a virtual telescope the size of Earth, captured the shadow of M87 star, a black hole 6.5 billion times the mass of our Sun, at the heart of a galaxy 55 million light-years away. 3 years later, the same collaboration produced an image of our own galactic center, Sagittarius A star. And in January of 2025, the LIGO Gravitational Wave Observatory recorded the clearest signal ever received from a black hole merger. 2 dead stars, each roughly 33 times the mass of the Sun, spiraling into each other 1.3 billion light-years away, shaking the fabric of space-time itself with a ripple so faint that detecting it required measuring a change smaller than 1/10,000th the width of a proton. We can see them now. We can hear them. We have photographed their shadows, listened to the ringing of their collisions, and tracked stars whipping around their invisible edges at thousands of kilometers per second. But the one thing we cannot do, the one thing no observation, no telescope, no detector can ever accomplish, is look inside. What happens behind the event horizon? What does the interior of a black hole actually look like? Is there a center, and if so, what is it made of? Does information survive in there, or is it erased from the universe forever? These are not minor questions. They sit at the exact intersection of the two most successful theories in the history of physics: general relativity, which describes gravity, space-time, and the architecture of the cosmos, and quantum mechanics, which describes atoms, particles, and the fundamental fabric of matter. Both theories work with extraordinary precision in their own domains. Both have been tested to staggering accuracy. And both, when applied to the interior of a black hole, produce answers that flatly contradict each other. That contradiction is not a failure. It is an invitation. There is something quietly profound about the fact that we know any of this. The universe evolved for 13.8 billion years in perfect silence. No witness, no record, no awareness. Stars formed and collapsed, galaxies merged, black holes grew, and none of it was observed because there was nothing capable of observing it. Then, in the last fraction of cosmic time, in the last 10,000% of the universe's existence, matter organized itself into something that could look back at the cosmos and ask what it was made of. That is what we are doing tonight, not merely recounting facts about exotic objects in distant space, but following a question to the place where our understanding breaks. The question is simple: what happens inside a black hole? The answer leads through collapsing stars and frozen clocks, through spaghettified astronauts and evaporating horizons, through paradoxes that have divided the brightest minds in physics for half a century. And at the end of that road, what we find is not a final answer, but the outline of a door we have not yet learned to open. The darkness inside a black hole is not the darkness of ignorance. It is the darkness of a question so deep that answering it may require reinventing our understanding of space, time, and information itself. And there is nothing small about that. The fact that the most powerful objects in the universe are also the ones that expose the limits of everything we know. That is not a humiliation. It is the universe telling us that the story is not finished, that the next chapter has not been written. We are going to follow that story tonight, from the death of a star to the edge of known physics and beyond. It is a long journey. If you find it pulling you towards sleep, that is fine. The universe will still be here in the morning, doing what it has always done, existing, evolving, waiting to be understood. But before we begin, if this is your first time here, or if you have been listening for a while and have never gotten around to it, consider subscribing. Not because an algorithm demands it, but because these documentaries take months to build, and every subscription tells us someone out there finds value in the work. And if you feel like it, leave a comment. Tell us where you are, what time it is there, what brought you to a documentary about black holes at this hour of the night. We read everyone. Now, let us begin at the only place a story about black holes can begin, with the death of a star. And the answer starts in 1930, on a ship crossing the Indian Ocean, in the notebook of a physicist who had not yet turned 20. In the autumn of 1930, a 19-year-old physics student named Subrahmanyan Chandrasekhar boarded a ship in Madras, bound for Cambridge. The voyage would take weeks. He had recently completed his undergraduate degree, he had a government scholarship in his pocket, and he had brought along a stack of papers on the physics of dying stars. Somewhere on the Indian Ocean, between the coast of India and the Suez Canal, he sat down with a pencil and began to calculate what happens to a star when its fuel runs out. The prevailing wisdom at the time was straightforward. Stars burn hydrogen. When the hydrogen is exhausted, the star contracts under its own gravity until a quantum mechanical effect, electron degeneracy pressure, a consequence of the Pauli exclusion principle, which forbids electrons from occupying the same quantum state, pushes back against the collapse. The star settles into a dense, Earth-sized remnant called a white dwarf and slowly cools for eternity. Every star, regardless of mass, was assumed to end this way. A quiet retirement after billions of years of nuclear burning. Chandrasekhar saw a problem. He included something his predecessors had neglected: special relativity. At high enough densities, the electrons inside a collapsing star would be squeezed so tightly that they would approach the speed of light. And when electrons become relativistic, something fundamental changes in the mathematics. The degeneracy pressure that was supposed to halt the collapse develops a ceiling. It can only push back so hard. Beyond a certain mass, roughly 1.4 times the mass of our Sun, the pressure loses the fight. The star cannot become a white dwarf. Gravity wins. Chandrasekhar had found a limit, and the question it raised was terrifying in its simplicity. If a star too massive to become a white dwarf cannot stop collapsing, what does it become? He presented this result at a meeting of the Royal Astronomical Society in 1935. The response came from Arthur Eddington, the most celebrated astrophysicist in Britain, the man who had confirmed Einstein's general relativity by measuring starlight bending around the Sun during the 1919 eclipse. Eddington stood up after Chandrasekhar's talk and dismissed the calculation entirely. His objection was not mathematical, it was aesthetic. He declared that there ought to be a law of nature preventing a star from behaving in this absurd way, collapsing without limit, contracting and contracting until gravity became strong enough to hold in its own radiation. The idea offended his sense of cosmic order. Eddington was wrong. Chandrasekhar was right, but it would take decades and a Nobel Prize, awarded in 1983, before the physics community fully accepted what that teenager on a ship had discovered, that nature does not share our preferences for tidy endings. The Chandrasekhar limit is the first domino in a chain that leads inevitably to black holes. But there is a middle step. Stars between roughly 8 and 25 solar masses do not simply skip from burning hydrogen to collapsing into oblivion. They go through a spectacular and violent process first. A massive star does not burn only hydrogen. As it ages, it fuses heavier elements in successive shells: helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon. Each new fuel ignites at a higher temperature and burns for a shorter time. Hydrogen burning sustains a star for millions of years. Silicon burning, the final stage, lasts about a single day, and the product of silicon fusion is iron. Iron is the end of the road. Every element lighter than iron releases energy when it fuses. Every element heavier than iron consumes energy to fuse. When iron accumulates in the core, the star has built its own death sentence, a ball of nuclear ash from which no further energy can be extracted. The core is supported by electron degeneracy pressure, the same force Chandrasekhar studied, but it is growing heavier by the hour as the silicon shell keeps raining iron onto it. When the core crosses the Chandrasekhar limit, roughly 1.4 solar masses, the electron pressure fails. What happens next takes less than a second. The core collapses. Not slowly, not gradually, catastrophically. In roughly 3/4 of a second, a sphere of iron the size of Earth, about 8,000 kilometers across, compresses to a ball of neutrons, roughly 19 kilometers in diameter. The outer layers of the star, still unaware that the floor has vanished beneath them, hang in space for a brief, surreal moment before crashing inward. The infalling material rebounds off the newly formed neutron core, and a shockwave tears the star apart in a supernova explosion that can briefly outshine the entire galaxy it lives in. The energy released in that fraction of a second exceeds what our Sun will produce over its entire 10 billion year lifetime. Not by a small factor, but by a factor of hundreds. Most of that energy escapes not as light, but as neutrinos, trillions upon trillions of nearly massless particles streaming outward through the debris, carrying the gravitational potential energy of the collapse with them. If the remnant core left behind is below roughly 2 to 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, analogous to Chandrasekhar's limit but for neutron stars, then neutron degeneracy pressure can halt the collapse. The result is a neutron star, a city-sized object so dense that a teaspoon of its material would weigh about 6 billion metric tons. But if the remnant is too massive, if the core exceeds even this second limit, then nothing in known physics can stop the contraction. Not electron pressure, not neutron pressure, not any force or interaction that has ever been measured in a laboratory. The collapse continues past the neutron star stage, past any stable configuration, past any point where our equations offer a foothold. The matter falls inward and does not stop. What forms is an object whose gravitational pull is so extreme that, within a certain radius, the escape velocity exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing that crosses that radius can ever return. No signal, no particle, no information of any kind. The boundary is invisible. There is no surface, no wall, no physical structure. It is a mathematical threshold beyond which the universe becomes a one-way street. Roger Penrose proved in 1965 that this outcome is not a quirk of idealized models. His singularity theorem, the work that would earn him the Nobel Prize in 2020, showed that once a trapped surface forms, once gravity becomes strong enough to bend all outgoing light rays back inward, the formation of a singularity is inevitable. No spin, no pressure, no asymmetry can prevent it. The collapse is a sentence with no appeal. Every element heavier than hydrogen and helium was forged inside a star. The calcium in your bones was made in a supernova. The oxygen in your lungs was fused in the core of a star that died before the sun was born. The iron in your blood, every atom of it, was assembled in the final hours of a massive star's life, in that brief, silicon-burning phase that lasts a single day before the core gives way. You are, in the most literal and precise sense, built from the debris of stellar collapse, and the process that created you, the death of massive stars, is the same process that creates black holes. The same physics, the same chain of events. The difference is only mass, a little less, and you get a neutron star and the elements of life scattered into space. A little more, and you get an object from which nothing escapes, not even the light needed to see it. That object, that absence, has a boundary, and understanding what that boundary is, what it means, and what happens when you cross it, requires looking at the strangest prediction Einstein's theory ever made. In December of 1915, Albert Einstein published the field equations of general relativity, a set of mathematical relationships that describe how mass and energy curve the geometry of space-time, and how that curved geometry, in turn, tells matter how to move. The equations were elegant, profound, and extraordinarily difficult to solve. Einstein himself did not believe exact solutions were likely to be found. He was wrong. Within weeks, a German physicist named Karl Schwarzschild found one. Schwarzschild was not sitting in a comfortable university office. He was serving as an artillery officer on the Eastern Front of the First World War, calculating ballistic trajectories by day and, apparently, solving Einstein's equations by night. In the final months of 1915, while sheltering from gunfire in the trenches, he derived the first exact solution to the field equations for the space-time outside a perfectly spherical, non-rotating mass. He sent the result to Einstein in a letter. Einstein presented it to the Prussian Academy of Sciences in January of 1916. Schwarzschild died 5 months later from a disease contracted at the front. He was 42. His solution contained a peculiarity. At a specific radius from the center of the mass, a radius that depends only on how much mass is present, the mathematics behaved strangely. The equations seemed to blow up. For decades, physicists debated whether this was a real physical feature of space-time or merely an artifact of the coordinate system being used, like the way a map of the Earth distorts the poles. It took until 1958 when David Finkelstein reinterpreted the Schwarzschild solution using a different set of coordinates to settle the question. The blow-up was not a physical singularity. It was a boundary, a perfectly smooth, perfectly invisible threshold in space-time. Finkelstein called it a perfect unidirectional membrane. Causal influences can cross it in only one direction. Today we call it the event horizon. The formula for the Schwarzschild radius, the radius at which the event horizon forms, is one of the most compact and consequential equations in all of physics. It says that the radius equals 2 times the gravitational constant, times the mass, divided by the speed of light squared. What that means, in plain terms, is that the size of a black hole's event horizon is directly proportional to its mass. Double the mass, double the radius. Simple, linear, almost disappointing in its elegance. But the numbers it produces are not disappointing at all. If you could somehow compress the entire mass of our Sun, all 2 times 10 to the 30th kilograms of it, into a sphere small enough to form a black hole, the event horizon would have a radius of about 3 kilometers. Not 3 million, not 3,000. 3. The distance you could walk in roughly 40 minutes. The entire Sun crushed into a ball smaller than a mid-sized city. The Earth is even more dramatic. Its Schwarzschild radius is approximately 9 millimeters, smaller than a marble, smaller than the nail on your little finger. Every mountain, every ocean, every continent, every living thing on this planet, compressed to a sphere you could hold between your thumb and forefinger if you could hold something infinitely dense, which you could not. At the other end of the scale, the supermassive black hole at the center of our galaxy, Sagittarius A star, has an event horizon radius of about 12 million kilometers, roughly a third of the distance from the Sun to Mercury. And M87 star, the black hole the Event Horizon Telescope photographed, has an event horizon diameter of about 40 billion kilometers. The orbits of all the planets in our solar system, from Mercury to Neptune, would fit comfortably inside it. These are the sizes of nothing. The event horizon is not a surface. There is no wall, no membrane you could touch, no material boundary of any kind. If you were falling toward a sufficiently large black hole, you would cross the event horizon without any local indication that anything had changed. No alarm, no flash, no sensation. The space-time around you would be curved, but not dramatically so. No more than the space-time near any other gravitating object of comparable size. The event horizon is defined not by what is there, but by what can no longer happen. Nothing that crosses it can ever send a signal back to the outside universe. There is a theorem in general relativity called the no-hair theorem, and it makes a claim so stark that it almost sounds like a philosophical statement rather than a physical one. It says that an isolated black hole, once it has settled into a stable state, is completely described by exactly 3 numbers: its mass, its electric charge, and its angular momentum, its spin. That is all. 3 numbers, and you know everything there is to know about the space-time geometry outside the event horizon. Think about what this means. A star is a fantastically complicated object. It has a chemical composition, a temperature profile that varies from its core to its surface, magnetic fields threaded through its plasma, convection currents churning its outer layers, sunspots and flares, and coronal mass ejections. A planet is even more complex. Oceans, atmospheres, tectonic plates, ecosystems, weather. A human being is so complex that no equation ever written could fully describe one. A black hole has 3 numbers. It does not matter what fell in to create it, whether it was a collapsing star made of hydrogen and helium, or a cloud of interstellar dust, or a collection of encyclopedias, or a fleet of starships. Once the material crosses the horizon and the black hole settles down, all that distinguishes the result from any other black hole of the same mass, charge, and spin is erased. The information about what went in appears to be gone, scrubbed from the exterior geometry as thoroughly as if it never existed. This is part of what makes black holes so profoundly unsettling to physicists. They are, in a sense, the simplest macroscopic objects in the universe, simpler than stars, simpler than planets, simpler than a grain of sand. John Wheeler, the physicist who popularized the term black hole in the late 1960s, summarized the no-hair theorem with a phrase that has become famous in the field: black holes have no hair, meaning no distinguishing features, no texture, no structure, no personality, just mass, charge, and spin. And for most astrophysical black holes, the charge is effectively zero, so really just mass and spin. The simplest objects in the cosmos, born from the most violent events in the cosmos. There is something almost unsettling about that combination, as if the universe, at its most extreme, defaults to minimalism. And it is this very simplicity that creates one of the deepest problems in modern physics. Because quantum mechanics insists that information can never be destroyed. And general relativity, through the no-hair theorem, insists that black holes destroy it. Both theories have been tested to extraordinary precision. Both have never failed a single experimental check. And yet, on this question, they cannot both be right. But that paradox is a story for later chapters. For now, what matters is the boundary, the event horizon, and what happens to anything that approaches it. Because the closer you get, the more space-time itself begins to warp, and the forces that act on your body start to do something that Stephen Hawking once described with a single, vivid, unforgettable word. The word is spaghettification. Stephen Hawking coined it, or at least brought it into common usage, to describe what happens to an object falling toward a black hole when the tidal forces become overwhelming. The image is crude, and intentionally so. Your body, stretched vertically and compressed horizontally, pulled into a long, thin strand, like a piece of pasta being drawn through the gravitational field of something with no mercy and no surface. It is not a dignified end, but it is a precise one, and the physics behind it connects to something as familiar as the ocean tides on Earth. Tidal forces are not about gravity itself. They are about the difference in gravity between 2 points. Right now, sitting or lying wherever you are, your feet are slightly closer to the center of the Earth than your head. The gravitational pull on your feet is therefore marginally stronger than the pull on your head. This difference is so small, about 5 millionths of a meter per second squared, that you never feel it. But the principle scales. The moon's tidal pull creates the twice-daily rise and fall of the oceans precisely because the side of Earth nearest the moon feels a stronger pull than the side farthest away. The planet itself is being gently stretched along the line connecting it to the moon and squeezed perpendicular to that line. Not enough to notice with your eyes, enough to move oceans. Now replace the moon with a stellar mass black hole, say 10 times the mass of the Sun, with a Schwarzschild radius of about 30 kilometers, and bring yourself close. The equation governing the tidal acceleration is clean. 2 times the gravitational constant, times the mass, times the length of the object, divided by the distance cubed. That cube in the denominator is what matters. As you approach the black hole, the tidal force does not merely increase. it erupts. At the event horizon of a 10 solar mass black hole, the difference in gravitational pull between the head and feet of a roughly 1.8 meter tall human would be approximately 19.6 billion meters per second squared. For context, a force of about 9,000 newtons is sufficient to pull a human body apart. At that tidal acceleration, you would not be stretched, you would be disassembled, and this would happen well before you reach the event horizon. At a distance of roughly 700 kilometers from the center, you would already be in serious trouble. The numbers are horrifying, but they contain a surprise. Do the same calculation for the supermassive black hole at the center of our galaxy. Sagittarius A star has a mass of about 4 million suns and an event horizon radius of approximately 12 million kilometers. At that horizon, the tidal acceleration on a human body drops to about 1.9 millionths of a meter per second squared. That is less than the tidal force you experience right now, sitting on the surface of the Earth. Significantly less. You could cross the event horizon of Sagittarius A star, the point of no return, the boundary beyond which you can never send a signal to the outside universe again, and you would feel nothing. No stretching, no discomfort, no indication whatsoever that anything had changed. This is one of the most counterintuitive results in black hole physics. The larger the black hole, the gentler the crossing. A stellar mass black hole would shred you to atoms long before you got near the horizon. A supermassive black hole would swallow you whole, and you would not notice until later. Much later, when the interior geometry tightened around you and the tidal forces, so mild at the horizon, began their inevitable climb toward infinity as you approached whatever lies at the center. The reason is the cubic scaling. Tidal forces depend on the distance cubed, and a supermassive black hole's horizon is vastly farther from its center than a stellar mass black hole's horizon is from its center. The gravitational gradient across your body is spread over a much larger distance, diluted by the sheer scale of the object. At a stellar mass black hole, the curvature of space-time is ferocious at the horizon. At a supermassive one, it is almost flat, locally indistinguishable from empty space. So if you ever find yourself with no choice but to fall into a black hole, choose the largest one available. The small ones kill you before you arrive. The large ones let you arrive and then kill you later. It is a grim sort of mercy, but in the physics of black holes, you take what you can get. We have spoken about hypothetical human bodies falling into black holes, which is a useful thought experiment, but not something the universe provides us with. What the universe does provide frequently is stars falling into supermassive black holes. And when that happens, the tidal forces do not care that the object is enormous. The physics is the same, only the scale has changed. When a star wanders too close to a supermassive black hole, the tidal gradient across its diameter can exceed the star's own gravitational cohesion, the force holding it together. The near side of the star is pulled harder than the far side. The star elongates, distorts, and finally tears apart in what astronomers call a tidal disruption event. The debris forms a long, luminous stream that wraps around the black hole, heats to millions of degrees through friction as it spirals inward and briefly flares in ultraviolet and X-ray light bright enough to be detected across billions of light years. These events are not rare. Surveys estimate that a typical galaxy experiences a tidal disruption roughly once every 10 to 100,000 years. In October of 2019, astronomers at the University of California, Berkeley, identified one of the closest examples ever recorded: a sun-like star, torn apart by a supermassive black hole in a spiral galaxy within the constellation Andromeda. The event was luminous enough to study in visible light for the first time, and it held a surprise. Most of the stellar debris was not swallowed by the black hole. It was flung outward, ejected at high velocity, as though the black hole had taken a bite and spat the rest back into space. Tidal disruption events are, in a sense, spaghettification made visible, not of a person, but of an entire star, played out over weeks rather than fractions of a second, broadcasting its destruction across the electromagnetic spectrum for anyone with the right telescope to witness. But tidal forces, as dramatic as they are, describe only what gravity does to space. A black hole does something equally strange to the other axis of reality, the one we measure with clocks rather than rulers, and what it does to time is, if anything, even harder to accept. Before we talk about black holes and time, it is worth remembering that time dilation is not science fiction. It is not a theoretical curiosity waiting for future experiments to confirm. It is happening right now, everywhere, all the time, including inside the phone in your pocket. The Global Positioning System relies on a network of satellites orbiting Earth at an altitude of about 20,000 kilometers. Each satellite carries an atomic clock precise to within a few billionths of a second per day. For the system to work, for your map application to place you on the correct street rather than a neighboring one, the clocks on those satellites must account for two relativistic effects. Special relativity predicts that moving clocks tick more slowly, which makes the satellite clocks lose about 7 microseconds per day relative to clocks on the ground. General relativity predicts that clocks in weaker gravitational fields tick faster, which makes the satellite clocks gain about 45 microseconds per day. The net effect is a gain of roughly 38 microseconds per day. If this correction were not applied, GPS positions would drift by approximately 10 kilometers every 24 hours. The system would be useless within a week. That is time dilation at the gentle curvature of Earth's gravity. A planet so gravitationally modest that its Schwarzschild radius is 9 millimeters. Near a black hole, the same effect does not merely accumulate, it dominates, it overwhelms. It rewrites the relationship between two observers so completely that they can no longer agree on what the word now means. Imagine two friends. One stays safely in orbit, far from a black hole. The other begins to fall inward. They each carry a clock, and at the start, both clocks agree perfectly. As the falling friend descends deeper into the black hole's gravitational well, the orbiting friend watches through a telescope and notices something disturbing. The falling friend's clock is slowing down, not by microseconds, as with GPS satellites, but visibly, measurably. The closer the falling friend gets to the event horizon, the more pronounced the effect becomes. Seconds on the falling clock stretch into minutes on the orbiting clock. Minutes stretch into hours. Hours into years. At the same time, the light from the falling friend is changing. Each photon climbing out of the gravitational well loses energy in the effort, and losing energy means its wavelength stretches, a phenomenon called gravitational redshift. Blue light shifts to red shifts to infrared. Infrared fades beyond what any detector could register. The falling friend is not only slowing down, but dimming and reddening, as though the universe were gently erasing them from visibility. And at the event horizon itself, from the orbiting friend's perspective, time dilation becomes infinite. The falling clock appears to stop entirely. The last photon emitted just outside the horizon is redshifted to a wavelength so long it carries effectively zero energy. The falling friend does not disappear in a flash or a bang. They fade, they redden, they freeze at the threshold, one final image stretched across the surface of the event horizon, growing dimmer and dimmer until no instrument in the universe could detect what remains. This is why black holes were once called frozen stars. Before the term black hole entered common usage, before John Wheeler popularized it in the late 1960s, Physicists described the collapsing remnant as an object whose surface appeared to any external observer to freeze at the Schwarzschild radius. The star never quite finished collapsing. It just asymptotically approached its own horizon, fading from view, suspended in a permanent state of almost. But the falling friend does not experience any of this. This is the part that resists intuition, the part where human experience fails as a guide. From the perspective of the person actually falling, nothing remarkable happens at the event horizon. Their clock keeps ticking at its normal rate. The seconds feel like seconds. If the black hole is large enough, supermassive, say like Sagittarius A star, the local space-time at the horizon is barely curved. There is no sign, no signal, no alarm. The event horizon is not a place you arrive at. It is a boundary you pass through, and you know you have passed through it only because you can no longer send a message back. The falling friend crosses the horizon in finite proper time. That is the technical phrase, proper time, meaning the time measured by the clock traveling with the observer. The crossing is smooth, continuous, unremarkable. And yet, from the perspective of every external observer, it never happens. The infalling observer is forever frozen at the horizon, forever dimming, forever just about to cross, but never quite crossing. Both descriptions are correct. Neither is an illusion. General relativity does not privilege one frame over the other. The orbiting friend's experience, watching the clock freeze, is as physically real as the falling friend's experience of passing through without incident. The theory simply tells us that time is not absolute, it is local. What one observer measures as an infinite duration, another measures as a few heartbeats, and neither of them is wrong. This is what makes black holes so disorienting. Not just the warping of space or the crushing of matter, but the warping of time itself. Two observers sharing the same universe, living through the same event, and yet experiencing durations so different that one of them ages by seconds while the other ages by eons. The falling friend might cross the horizon while outside, entire civilizations rise and fall, stars exhaust their fuel, and galaxies drift apart. Or at least, that is what the mathematics suggests. No one has ever tested this prediction near an actual event horizon, but the milder version, the version playing out in GPS satellites 20,000 kilometers above your head, the version measured by atomic clocks at different altitudes in a building, the version confirmed by every precision experiment ever conducted, has never once been wrong. There is no reason to believe it stops being right when the gravitational field gets stronger, and near a black hole, it gets as strong as the universe allows. So what does the falling observer see in those final moments of approach? The external universe does not vanish. Quite the opposite, it accelerates. Light falling inward from the cosmos is blue-shifted, compressed into higher energies. The entire history of the external universe, all its future light, piles up and floods in. Whether a human brain could process any of this is a separate question entirely, and not one general relativity is equipped to answer. What general relativity can tell us is what lies ahead for the falling observer, beyond the event horizon, past the point of no return, into the interior of the black hole. And the answer depends on what kind of black hole you have fallen into. A simple, non-rotating Schwarzschild black hole presents one fate. A rotating Kerr black hole, which is what most real black holes are believed to be, presents something far stranger. A labyrinth of nested horizons, a ring-shaped singularity, and geometric structures so exotic that drawing them on paper required the invention of an entirely new kind of diagram. Let us be clear about something before we go any further. When we say you can fall through the event horizon without noticing, we are not being poetic. We are not simplifying for the sake of a good story. The mathematics of general relativity makes an unambiguous prediction. For a sufficiently massive black hole, the crossing of the event horizon is a non-event. The curvature of space-time at the horizon of a supermassive black hole is gentle. The tidal forces are negligible. There is no surface to collide with, no energy barrier to punch through, no membrane to tear. The event horizon is not a thing. It is a consequence, a geometric property of space-time that separates events that can still communicate with the outside universe from events that cannot. You would not feel the crossing. You would not see it. There is no flash, no boundary line painted across space, no change in the local texture of reality. If you closed your eyes for a moment during the fall and opened them again, you would have no way of knowing whether you had crossed the horizon or not. The only clue would come if you tried to send a signal outward, a radio pulse, a beam of light, a shout into the void, and realized that no matter how hard you tried, no matter which direction you aimed, the signal always curved back inward. Not because something was blocking it, but because the geometry of space-time itself now points every possible path toward the center. That is the true horror of the event horizon, if horror is the right word. It is not violent, it is not dramatic, it is absolute. Once inside, there is no trajectory, no velocity, no engine that could carry you back. Moving outward is no longer a direction you can travel, in the same way that moving backward in time is not a direction you can travel in ordinary space-time. The event horizon converts a dimension of space into something that behaves like a dimension of time. What was once inward toward the center becomes forward into the future. Reaching the singularity is not a matter of moving to a place. It is a matter of waiting. It will come to you inevitably the way tomorrow comes to you now. While the crossing itself is smooth, the view is not ordinary. As you fall, the universe behind you, the stars, the galaxies, the cosmic background, does not simply recede, it distorts. Light from every direction is bent by the black hole's gravity, and the visual effect is a kind of gravitational funhouse. Objects behind the black hole can be seen multiple times, their images wrapped around the warped geometry. Stars that should be hidden on the far side appear above and below, as if space-time has folded the sky like a piece of paper. Ahead of you, the black hole's shadow grows. It starts as a dark patch against the background of stars, circular and featureless, and it swells as you approach. The boundary of that shadow is not the event horizon. It is the photon sphere, a shell at 1.5 times the Schwarzschild radius, where light can orbit the black hole in unstable circles, tracing paths that neither escape nor fall in. Any closer, and even light aimed directly outward will spiral inward. As you cross the horizon, something peculiar happens to the geometry of that shadow. Computer simulations, particularly those developed by Andrew Hamilton at the University of Colorado, show that the dark region ahead does not simply envelop you, it appears to split. The event horizon, seen from the outside, was a single dark sphere. From the inside, as you pass through, it seems to separate into two surfaces, one ahead, one behind. The universe outside does not vanish from your view. It compresses into a shrinking bright ring above you, a window back to the cosmos that narrows as you fall deeper, admitting light that is increasingly blue-shifted, compressed to higher energies by the extreme gravitational gradient. Whether a human visual system could process any of this is doubtful. The blue-shifted radiation pouring in from the outside universe would climb through visible wavelengths into ultraviolet, then X-rays, then gamma rays. Long before the view became philosophically interesting, it would become physically lethal. But the mathematics does not concern itself with the fragility of human eyes. It simply describes the paths that light takes through curved space-time, and those paths produce a picture unlike anything the universe offers elsewhere. Inside the horizon of a Schwarzschild black hole, the simplest kind, non-rotating and uncharged. There is nowhere to go but down. Every future-directed path leads to the singularity. You cannot orbit, you cannot hover, you cannot even slow your approach, because slowing down would require moving in a direction that no longer exists within the geometry. The singularity is not a place in front of you. It is a moment ahead of you, a future you cannot avoid, approaching at the speed of causality itself. The time remaining, measured by your own clock, depends on the mass of the black hole. For a black hole the mass of our Sun, the journey from horizon to singularity would last roughly 10 microseconds, barely enough time for a nerve signal to travel from your hand to your brain. For Sagittarius A star, you would have about 20 seconds. For M87 star, the supermassive giant in the Virgo cluster, you might have several hours. Hours. Falling through the interior of a black hole, with the outside universe compressed into a fading ring of light above you, and the singularity, the edge of known physics, approaching with the patience of an appointment you cannot cancel. That is the interior of a Schwarzschild black hole. One way in, no way out. One destination, no exceptions. But most black holes in the universe are not Schwarzschild black holes. Most of them spin. They drag space-time around with them as they rotate, twisting it like honey wound around a turning spoon. And a spinning black hole, described by the Kerr solution, found by New Zealand mathematician Roy Kerr in 1963, has an interior that is not a simple tunnel to a point. It is an architecture. It has structure, layers, nested horizons, and at its center, not a point of infinite density, but a ring. A ring of infinite curvature, yes, but a ring nonetheless, with an interior that the mathematics says you could, in principle, pass through. Into what, the equations do not reliably say, but they suggest possibilities that sound more like science fiction than science. And understanding why requires a new tool, a new kind of map, and a willingness to follow the geometry wherever it leads. In 1963, a mathematician from New Zealand named Roy Kerr did something that had eluded physicists for nearly half a century. He found an exact solution to Einstein's field equations for a rotating mass. The Schwarzschild solution, published in 1916, described the space-time around a mass that does not spin, an idealized case, elegant but unrealistic, since virtually everything in the universe rotates. Stars spin, planets spin, galaxies spin. Any black hole formed from a collapsing star inherits the angular momentum of that star, and angular momentum is conserved. It does not disappear. A collapsing star that was rotating slowly will produce a black hole rotating quickly because the same angular momentum is compressed into a far smaller object, like a figure skater pulling their arms in and spinning faster. Kerr's solution changed the picture entirely. A Schwarzschild black hole has a single event horizon and a point singularity at its center. A Kerr black hole has layers. The outermost structure is the ergosphere, a region outside the event horizon where space-time is dragged so forcefully by the black hole's rotation that nothing, not even light, can remain stationary. You can enter the ergosphere and leave again, but while you are inside, you are compelled to co-rotate with the black hole, whether you want to or not. Space-time itself is in motion there, flowing like a river around the drain, and no engine or thrust could hold you still against that current. Beneath the ergosphere lies the outer event horizon. This is the point of no return, functionally equivalent to the Schwarzschild horizon, the boundary beyond which no signal can reach the outside. Cross it, and you are inside the black hole. But in a Kerr black hole, there is more. Below the outer horizon lies a second boundary, the inner horizon, also called the Cauchy horizon. This is where the map of the interior becomes deeply, almost philosophically strange. To understand the Cauchy horizon, you need to understand what physicists mean by determinism. In classical physics and in general relativity, the universe is deterministic. If you know the complete state of a system at one moment in time, you can, in principle, calculate its state at every future moment. The equations run forward, and they give exactly one answer. This is what allows us to predict eclipses, design bridges, and send spacecraft to the outer planets. The laws of physics, given sufficient information, tell you what happens next. The Cauchy horizon is the surface beyond which that guarantee breaks down. Below the inner horizon of a Kerr black hole, the equations of general relativity no longer produce a single, unique future. They produce many possible futures, infinitely many, in fact. The geometry becomes what mathematicians call non-globally hyperbolic, which is a technical way of saying that the usual rules for predicting the future from the past no longer apply. Initial conditions on one side of the Cauchy horizon do not uniquely determine what happens on the other side. This is not a small problem. It means that below the Cauchy horizon, physics as we practice it, the entire framework of writing down equations, feeding in initial conditions, and reading off predictions, stops working. Not because the equations become too difficult to solve, because they become ambiguous. They offer multiple answers where only one can be correct, and provide no mechanism for choosing among them. Whether the Cauchy horizon actually exists in real astrophysical black holes is one of the most actively debated questions in general relativity. Many physicists believe it is unstable, that any infalling matter or radiation would pile up at the Cauchy horizon and create what is called a mass inflation singularity, effectively destroying the inner horizon before any observer could cross it. Others argue that the singularity formed might be weak enough to survive, that an observer might pass through it battered but intact, like a ship crossing a turbulent reef into calmer waters beyond. Penrose, characteristically, had something to say about this. His strong cosmic censorship conjecture proposes that the Cauchy horizon is generically unstable, that nature does not permit the kind of ambiguity it represents. In Penrose's view, the universe protects determinism by ensuring that the interior of a real, perturbed Kerr black hole destroys the Cauchy horizon before anyone can benefit from crossing it. The conjecture remains unproven. Counterexamples have been proposed. The debate continues. At the very center of a Kerr black hole, if the idealized mathematics is to be taken at face value, the singularity is not a point, it is a ring. A one-dimensional loop of infinite curvature lying in the equatorial plane of the rotating black hole, with a finite radius determined by the black hole's angular momentum. And unlike the point singularity of a Schwarzschild black hole, which every infalling trajectory must strike, the ring singularity of a Kerr black hole can, in principle, be avoided. An object falling along the axis of rotation could pass through the center of the ring without hitting it. What lies on the other side? The equations permit something extraordinary. Passing through the ring singularity, according to the Kerr solution, leads into a new region of space-time, one that is not the universe you came from, and not the interior of the black hole. It is, mathematically speaking, another universe entirely. The Kerr geometry, when fully extended, contains an infinite chain of alternating universes and black hole interiors, each connected by ring singularities, the whole structure repeating endlessly like the reflections in two parallel mirrors. No serious physicist believes this is what the interior of a real astrophysical black hole looks like. The fully extended Kerr solution is an idealization, an eternal, uncharged, perfectly axisymmetric vacuum solution perturbed by nothing. Real black holes form from collapsing matter, are bathed in radiation, and are surrounded by accretion disks and infalling debris. The delicate interior structures predicted by the exact Kerr geometry would almost certainly be disrupted by the slightest perturbation. The Cauchy horizon, as we discussed, may be unstable. The passage through the ring singularity may not survive contact with reality. But the fact that the equations permit these structures, that general relativity, taken at its word, produces geometries containing wormholes, alternate universes, and paths through singularities, tells us something important. It tells us that we are operating at the boundary of what the theory can describe. The interior of a rotating black hole is where general relativity begins to speak in a language that may no longer correspond to the physical world. It is a map that has become more detailed than the territory it was meant to represent. And when a map contradicts the territory, it is the map that must yield. To understand what actually happens at the center of a black hole, at the singularity, whether point or ring, we need a theory that general relativity cannot provide. We need a quantum theory of gravity. And the first hint that such a theory was necessary came not from the center of a black hole, but from its edge, from the event horizon, where Stephen Hawking discovered that black holes are not, after all, perfectly black. We need to talk about the singularity, not around it. Not in metaphors designed to soften the problem. The singularity is where the story of general relativity reaches its own ending, where a theory that has correctly described every gravitational phenomenon we have ever measured produces an answer that it cannot explain. Here is what general relativity predicts. At the center of a non-rotating black hole, all the mass that ever fell through the event horizon is compressed into a single point of zero volume and infinite density. The curvature of space-time, which elsewhere in the universe is a smooth and finite quantity, diverges. It goes to infinity. The mathematical framework that describes how particles move, how light bends, how clocks tick, all of it becomes undefined at that point. Not approximately undefined, not very large. The equations divide by zero. They produce outputs that have no physical interpretation, and they offer no prescription for what happens next. This is what physicists mean when they say the singularity is where physics breaks down. They do not mean that strange things happen there. Strange things happen everywhere inside a black hole. They mean that the theory itself, the language, the mathematics, the conceptual framework, cannot construct a sentence about what the singularity is. It is not that we lack data, it is that the tools we possess are structurally incapable of producing an answer. Roger Penrose's singularity theorem, published in 1965, established that this breakdown is not a fluke of oversimplified models. Earlier analyses of gravitational collapse had assumed perfect spherical symmetry, a star collapsing uniformly from all sides, with no turbulence, no magnetic fields, no rotation. One could argue that the singularity appearing in those models was an artifact of the artificial tidiness of the setup. Perhaps a real, messy, asymmetric collapse would produce something different. The matter might overshoot, or the pressure might halt the contraction at some finite density. Penrose proved this hope was wrong. His argument relied on a concept he invented for the purpose: the trapped surface. A trapped surface is a closed two-dimensional region in space-time where all outgoing light rays are converging, even the ones aimed outward. Under normal circumstances, a sphere of light emitted from a point expands outward, growing larger over time. On a trapped surface, both the inward and outward pointing light rays are converging. Space-time has curved so severely that there is no outward direction anymore. Every photon, no matter which way it was launched, moves towards smaller spheres. Penrose showed that once a trapped surface forms, and this requires only the mild assumption that gravity is always attractive, which is equivalent to saying that energy is never negative, then somewhere in the future of that surface, space-time must be geodesically incomplete. That is the formal term. It means that at least one path through space-time, followed by a freely falling particle or a beam of light, reaches an endpoint in finite time and cannot be extended further. The path simply terminates. The particle arrives at a boundary of space-time beyond which the theory has nothing to say. Penrose was careful about what his theorem does and does not prove. It proves that something goes wrong, that the space-time develops a hole, a place where trajectories end. It does not prove that the curvature becomes infinite at that place. It does not describe the shape or nature of the singularity. It does not say whether the singularity is a point, a surface, a space-like boundary, or something else entirely. And critically, it does not prove that an event horizon must surround the singularity. The theorem leaves open the alarming possibility that singularities could be naked, visible to the outside universe, their incomprehensible physics exposed for all to see. This last possibility troubled Penrose enough that he proposed in 1969 what he called the cosmic censorship conjecture. The weak form states that singularities formed by gravitational collapse are always hidden behind event horizons, that nature does not permit naked singularities. The strong form, proposed in 1979, goes further. It states that the region of space-time accessible to any observer is always deterministic, always well-behaved, always governed by equations that produce unique predictions. Both forms of the conjecture remain unproven. Over 50 years of effort by some of the most capable mathematicians and physicists in the world have produced partial results, special cases, and numerical simulations that support the conjecture, but no general proof. Counterexamples exist in contrived settings, and whether they can arise from realistic physical processes is not settled. Cosmic censorship is, as one physicist described it, the most important unsolved problem in classical general relativity. If the conjecture is true, then the singularity is forever hidden. It is physically real, the theory demands it, but it is censored from observation by the event horizon. We can never see it, probe it, or receive any signal from it. It exists only inside the black hole, behind the one-way door, shielded from the rest of the universe. If the conjecture is false, then there exist processes in nature that expose the singularity to the outside. And since the singularity is where our equations lose their meaning, a naked singularity would represent a region of the cosmos where the future is genuinely unpredictable, not in the quantum mechanical sense of being probabilistic, but in the deeper sense of not being determined by any theory we possess. There is a question that deserves to be stated plainly, even if it has no answer yet. What is actually there? Most physicists believe the singularity is not a real physical object. It is a signal, a warning light on the dashboard of general relativity, indicating that the theory has been pushed beyond its range of validity. In the same way that Newtonian gravity breaks down at velocities near the speed of light and must be replaced by general relativity itself is expected to break down at the energy densities and curvature scales found at the center of a black hole. The replacement, whatever completes the picture, must be a theory of quantum gravity, a framework that incorporates both the geometric description of space-time from general relativity and the probabilistic, discrete structure of quantum mechanics. No such theory exists in complete form. String theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety. These are candidates, proposals, programs of research, not finished theories. Each offers partial insights. None has been tested against experiment. None produces a definitive, universally accepted picture of what replaces the singularity at the center of a black hole. What we know, the only thing we know with reasonable confidence, is that the singularity as described by general relativity is not the end of the story. It is a placeholder for physics we have not yet discovered. The equations break there, but the universe presumably does not. Something happens at those densities, at those curvatures, in that extreme regime where quantum effects and gravitational effects become equally important. Something replaces the point of infinite density. We just do not know what. And the first concrete evidence that quantum mechanics and black holes interact in a profound and unexpected way did not come from the singularity at all. It came from the horizon, from a calculation Stephen Hawking performed in 1974 that shocked even Hawking himself and set off a debate that has not yet ended. In the autumn of 1973, Stephen Hawking traveled to Moscow to meet the Soviet physicists Yakov Zeldovich and Alexei Starobinsky. The Soviets had been working on an intriguing idea that rotating black holes might create particles from the quantum vacuum, that the spin of a black hole could generate radiation in much the same way that a rotating metal sphere emits electromagnetic waves. Their mathematics was suggestive but incomplete, and Hawking was skeptical. He returned to Cambridge, determined to prove them wrong. Instead, he proved something far more radical. Over the following months, Hawking applied the machinery of quantum field theory, the mathematical framework that describes how particles and fields behave, to the curved space-time around a black hole. He was not looking at the singularity or the deep interior. He was looking at the event horizon, that smooth and seemingly featureless boundary where nothing dramatic was supposed to happen. And what he found was that the horizon radiates, not because of the black hole's rotation. Even a perfectly non-rotating Schwarzschild black hole would do it. The radiation was a consequence of something more fundamental, the interaction between quantum fields and curved spacetime. The result appeared in a short paper published in Nature in March of 1974 under the deliberately provocative title Black Hole Explosions. In it, Hawking showed that a black hole emits thermal radiation with a specific temperature, a specific spectrum identical to the glow of a heated object. Black holes are not black. They shine. Faintly, absurdly faintly, but they shine. The mechanism behind Hawking radiation is often explained using a picture that Hawking himself popularized, and that Hawking himself later admitted was misleading. The popular version goes like this. Quantum mechanics allows pairs of virtual particles to constantly pop in and out of existence near the event horizon. Normally, the pair annihilates almost instantly. But at the horizon, one particle might fall in while the other escapes, and the escaping particle becomes real radiation, carrying energy away from the black hole. It is a vivid image. It is also, in important ways, wrong. The actual physics does not involve virtual particles becoming real in the way the analogy suggests. There are no antiparticles carrying negative energy falling into the black hole to reduce its mass. What is really happening is more subtle and, in its way, more beautiful. Quantum fields exist everywhere in spacetime. In flat, empty space, these fields sit in what physicists call the vacuum state, their lowest energy configuration. But the definition of vacuum depends on who is measuring it. An accelerating observer in flat spacetime perceives the vacuum as being filled with thermal radiation, a phenomenon called the Unruh effect, predicted by William Unruh in 1976. The temperature of this radiation depends on the acceleration. Near the event horizon of a black hole, an observer who hovers at a fixed distance, resisting the pull of gravity, accelerating constantly to avoid falling in, must accelerate enormously. And that acceleration means that what looks like empty space to a freely falling observer looks like a bath of hot particles to the hovering one. The radiation that the hovering observer detects is the Hawking radiation. It is not being created at the horizon in any localized sense. It is a manifestation of the fact that the concept of particle is not absolute in quantum field theory. It depends on the state of motion of the observer and the curvature of the spacetime they inhabit. The result is thermal radiation emanating from the vicinity of every black hole with a temperature inversely proportional to its mass. The formula is compact. The Hawking temperature equals h bar times c cubed divided by 8 pi times the gravitational constant times the mass times the Boltzmann constant. A black hole with the mass of our Sun would have a Hawking temperature of approximately 60 billionths of a Kelvin, about 10 million times colder than the cosmic microwave background, which itself is only 2.7 Kelvin. This is, by an enormous margin, colder than anything that has ever been measured, colder than anything that could plausibly be detected with current or foreseeable technology. In practical terms, stellar and supermassive black holes are gaining energy from their surroundings, absorbing photons from the cosmic microwave background, swallowing gas and dust. Far faster than they are losing it through Hawking radiation, they are growing, not shrinking. The radiation is real, but it is drowned out by the environment, like a whisper in a hurricane. But this will not always be the case. The universe is expanding, and as it expands, it cools. The cosmic microwave background, currently at 2.7 Kelvin, will continue to decrease in temperature as space stretches. Eventually, trillions of years from now, the background radiation will cool below the Hawking temperature of even the most massive black holes. When that happens, black holes will begin to lose mass faster than they gain it. They will shrink. And as they shrink, something remarkable occurs. A black hole's temperature rises as its mass decreases. A lighter black hole is a hotter black hole, and a hotter black hole radiates faster, which makes it lighter, which makes it hotter, which makes it radiate faster still. The process is a runaway, a positive feedback loop that accelerates as the black hole diminishes. The evaporation starts immeasurably slowly and ends in a catastrophe. The timescales are beyond human comprehension. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate, a number so large that writing it out would require 67 zeros after the one. The current age of the universe, 14 billion years, does not even register as a rounding error on that scale. A supermassive black hole of 100 billion solar masses would endure for roughly 10 to the power of 100 years. These are durations that make the word eternity feel inadequate, and yet they are finite. Given enough time, every black hole evaporates. The final moments are violent. The temperature climbs, the radiation output surges, and the black hole ends its existence in a burst of high-energy particles. What happens in the very last instant, when the black hole shrinks to the Planck mass, about 22 micrograms, the mass of a grain of pollen, is unknown. The physics at that scale requires a theory of quantum gravity, which we do not yet possess. But the slow death of a black hole through Hawking radiation created a problem far more urgent than the question of how the final instant plays out. Hawking's calculation showed that the radiation is thermal. Its spectrum depends only on the black hole's temperature, which depends only on its mass. It carries no information about what fell in, not what kind of star collapsed to form the black hole, not what objects were swallowed over the eons, not anything. The radiation is as featureless as the glow of a hot coal. It tells you the temperature and nothing else. If this is correct, then when a black hole evaporates completely, every record of everything that ever fell into it is gone, not hidden, not scrambled, erased from the universe. And that conclusion collides head-on with one of the most fundamental principles in all of physics. Quantum mechanics has a rule. It is not a suggestion, not a guideline, not an approximation that works most of the time and fails at the edges. It is, as far as anyone has ever been able to determine, absolute. The rule is this: information is never destroyed. What does that mean in practice? Imagine you burn a book. The pages blacken, curl, and crumble to ash. The words are gone. The ink is gone. The paper is gone. But the information, the precise arrangement of atoms that made up that book, is not gone. It has been transformed, scattered, redistributed into smoke particles, carbon dioxide molecules, infrared radiation, and thermal motion in the surrounding air. In principle, with a sufficiently powerful computer and a sufficiently complete record of every molecule's position and momentum, you could reconstruct the book from its ashes. Not in practice. The task would be absurdly, cosmically beyond any conceivable technology. But in principle, the laws of physics allow it. The information still exists, encoded in the state of the universe, and will exist forever. This is what physicists call unitarity, the requirement that quantum mechanical evolution preserves information. A pure quantum state evolves into another pure state, never into a mixed state, never into randomness, never into a configuration from which the original state cannot, even in principle, be recovered. Unitarity is not an optional feature of quantum mechanics. It is the load-bearing wall. Remove it, and the entire structure becomes inconsistent. Probabilities stop adding up to 1, the past becomes unrecoverable from the future, and the mathematical framework that describes every atom in your body collapses. Hawking's calculation said black holes violate this rule. The argument was straightforward, and that was what made it so devastating. A black hole forms from a collapsing star, a star with a detailed, specific quantum state, encoding the position and momentum of every particle it contained. That information crosses the event horizon and disappears behind it. The black hole settles down, and by the no-hair theorem, its exterior is characterized by only 3 numbers: mass, charge, and spin. All the details of the star, its composition, its temperature profile, its magnetic field structure, are inaccessible. Then the black hole begins to radiate. Hawking's calculation showed that this radiation is thermal, a perfect black body spectrum, determined solely by the black hole's temperature. Thermal radiation, by definition, carries no information beyond the temperature itself. It is as featureless as the hum of a space heater. 2 black holes of identical mass will produce identical radiation regardless of what fell into them, whether it was a star, a planet, or the collected works of Shakespeare. Now let the black hole evaporate completely. At the end of the process, all the mass energy that was once inside the black hole has been converted into Hawking radiation. But that radiation is thermal. It encodes nothing about the original state. The information that described the collapsing star, every quantum number, every correlation, every detail, is not hidden in the radiation. If Hawking was right, it is simply gone. A pure state has evolved into a mixed state. Unitarity has been violated. Hawking did not shy away from this conclusion. In a 1976 paper titled "Breakdown of Predictability in Gravitational Collapse," he argued explicitly that black hole formation and evaporation is a process in which quantum information is irreversibly lost. He framed it as a fundamental feature of quantum gravity, a sign that the union of general relativity and quantum mechanics would require modifying quantum mechanics itself. Most physicists found this unacceptable, not because they thought Hawking's calculation was wrong, the calculation was widely regarded as correct within its domain, but because the conclusion was too destructive. If information can be lost in black holes, then unitarity is not a fundamental law. And if unitarity is not fundamental, then the entire framework of quantum mechanics, the most precisely tested theory in the history of science, rests on uncertain ground. The theory that explains how transistors work, how atoms bond, how the sun shines, all of it would need to be rebuilt from a new foundation. In 1997, Hawking and Kip Thorne made a public bet with the theoretical physicist John Preskill. Hawking and Thorne wagered that information is genuinely lost in black holes. Preskill bet that it is not, that some mechanism not yet understood ensures the information comes back out. The stakes were an encyclopedia of the winner's choice, which Preskill interpreted as symbolizing the information that might or might not survive. The bet crystallized the divide. On one side stood Hawking's argument, rigorous, semi-classical, and leading to a conclusion that most physicists could not accept. On the other side stood a conviction held by much of the quantum gravity and string theory community that unitarity must be preserved, that the information gets out somehow, even if no one could explain the mechanism. Don Page, a physicist who had been Hawking's doctoral student in the 1970s, sharpened the debate in 1993 with a deceptively simple observation. If black hole evaporation is unitary, if the information does come out, then the entanglement entropy of the Hawking radiation must follow a specific curve. Early in the evaporation, when the black hole is large and has emitted little radiation, the entropy of the radiation increases steadily. Each new photon emitted is entangled with the black hole interior, and the entanglement grows. But at a certain point, roughly the halfway mark of the evaporation, when the black hole has lost about half its original mass, the entropy must begin to decrease. From that point on, each new photon must be correlated not only with the black hole, but with the previously emitted radiation. The new photons start to purify the radiation rather than increase its disorder. By the time the black hole has evaporated completely, the radiation must be in a pure state, zero entropy, all information recovered. This trajectory, entropy rising to a peak and then falling back to zero, is called the Page curve. If black hole evaporation follows the Page curve, unitarity is preserved. If it follows Hawking's original prediction, entropy rising monotonically, never decreasing, then information is lost. For 26 years after Page published his argument, no one could derive the Page curve from a gravitational calculation. Hawking's framework produced only the monotonically rising result. The Page curve remained a hope, a requirement imposed by faith in quantum mechanics, but not a prediction derived from any theory of gravity. In 2004, Hawking conceded the bet. At a conference in Dublin, he announced that he had changed his mind, that he now believed information is preserved, influenced in part by developments in string theory and the ADS/CFT correspondence, which we will come to shortly. He presented Preskill with an encyclopedia of baseball. Thorne did not concede, though he later did as well. But Hawking's concession, gracious as it was, did not solve the problem. Saying information gets out is not the same as explaining how. The mechanism remained a mystery, and the Page curve remained underived. The paradox was acknowledged but not resolved. Then, in 2019, two groups of physicists, working independently, using ideas drawn from quantum information theory, holography, and the geometry of space-time, produced a gravitational calculation that, for the first time, reproduced the Page curve. The information, it seemed, does get out. And the key to understanding how involved something no one had expected to find inside a black hole: islands. To understand the breakthrough that arrived in 2019, we need to step back and look at a development from 22 years earlier, one that changed the landscape of theoretical physics more profoundly than any single result since general relativity itself. In 1997, Juan Maldacena, a young Argentine physicist working at Harvard, proposed a conjecture so ambitious that many of his colleagues initially dismissed it as too good to be true. He argued that a theory of quantum gravity in a specific type of curved spacetime, called anti-de Sitter space, a universe with a negative cosmological constant that curves spacetime inward, like the interior of a saddle, is exactly equivalent to a quantum field theory living on the boundary of that space-time. Not approximately equivalent, not similar in some loose, hand-waving sense, exactly equivalent in the way that the same novel can be written in two different languages and still tell precisely the same story. This is the ADS/CFT correspondence, anti-de Sitter space/conformal field theory. On one side you have gravity, space-time, black holes, the full machinery of general relativity and its quantum extensions. On the other side you have a quantum field theory with no gravity at all, defined on a surface one dimension lower, obeying ordinary quantum mechanical rules. The two descriptions contain identical information. Anything you can calculate on one side, you can in principle calculate on the other. The implications for black holes were immediate and far-reaching. The boundary theory, the conformal field theory, is an ordinary quantum system. It obeys unitarity. Information cannot be lost. If ADS/CFT is correct, then any process described in the gravitational bulk, including the formation and evaporation of a black hole, must also be unitary because it has an equivalent description in a theory where unitarity is guaranteed. This was not a proof that information escapes from black holes. It was something subtler, a demonstration that, within the framework of string theory's best understood example of quantum gravity, information loss is mathematically impossible. The paradox was not resolved so much as cornered. Physicists now had strong reasons to believe the information gets out. What they still lacked was a concrete mechanism, a calculation performed on the gravity side, showing how the information makes its way into the radiation. That mechanism arrived 22 years later, and it involved a formula, a surface, and a region of space-time that should not, by any naive reasoning, be connected to the radiation at all. The story begins with a formula for entropy, not the thermodynamic entropy of a gas or a steam engine, but the entanglement entropy of a quantum system. In 2006, Shinsei Ryu and Tadashi Takayanagi proposed a remarkably simple prescription for calculating entanglement entropy in the ADS/CFT framework. If you want to know the entanglement entropy of a region on the boundary, you find the minimal area surface in the bulk that is anchored to the boundary of that region. The entropy is proportional to the area of that surface, divided by 4 times Newton's gravitational constant. The same formula that gives the Bekenstein-Hawking entropy of a black hole, but now applied to any region. The Ryu-Takayanagi formula was elegant, powerful, and widely confirmed in special cases, but it was a classical formula. It did not account for quantum corrections in the bulk. In subsequent years, physicists generalized it to what is called the quantum extremal surface prescription. Instead of finding the minimal area surface, you find the surface that extremizes a combination of the area and the quantum entanglement entropy of the fields across it. This generalized version is essential for understanding evaporating black holes, because quantum effects are precisely what drive the evaporation. In 2019, 2 landmark papers appeared. One, by Netta Engelhardt and Aaron Wall, building on earlier work, formalized the quantum extremal surface prescription. The other pair, by Ahmed Almhairi, Thomas Hartmann, Juan Maldacena, Edgar Shagulian, and Amir Hossein Tajdini in one paper, and by Jeffrey Pennington in another, applied these ideas to evaporating black holes and found something extraordinary. When a black hole is young and has emitted only a small amount of radiation, the quantum extremal surface that dominates the entropy calculation sits at the boundary of the black hole, essentially at the event horizon. The entanglement entropy of the radiation is computed from this surface, and it increases steadily with each photon emitted, just as Hawking predicted. So far, nothing new, but after the page time, roughly the halfway point of the evaporation, a new quantum extremal surface appears. This surface lies just inside the event horizon, slightly in the black hole's past. and the region it bounds, a region of the black hole interior that this surface encloses, is called an island. The island is the key to everything. What the calculation shows is that, after the page time, the entropy of the Hawking radiation should be computed not by tracing over the black hole interior as if it were entirely disconnected from the radiation, but by including the island, a piece of the black hole's interior, as part of the radiation's entanglement wedge. In plain language, after the halfway point of evaporation, a portion of the black hole's interior becomes, in a quantum information sense, encoded in the radiation that has already been emitted. The inside and the outside are not separate. They share a hidden quantum connection. When you compute the entropy including the island contribution, the result changes dramatically. Instead of climbing forever, the entropy reaches a peak at the page time and then begins to decrease, tracking the shrinking area of the black hole. The page curve emerges naturally from a gravitational calculation, without any ad hoc assumptions, without any modifications to quantum mechanics or general relativity. The mathematics itself produces the unitary answer. The mechanism by which this happens involves what are called replica wormholes, contributions to the gravitational path integral in which multiple copies of the spacetime are connected by tiny wormholes. These wormholes are not traversable. You cannot send signals through them. They do not create shortcuts between distant regions, but they alter the topology of the calculation in a way that produces the island and recovers the page curve. They are a mathematical structure in the path integral, not a physical tunnel. But their effect on the entropy is physical and concrete. The result has since been extended. In 2024, researchers applied the island formula to rotating Kerr black holes and obtained consistent page curves. Other groups have explored island configurations in charged black holes, in cosmological spacetimes, and in various dimensions. The framework is proving robust, but it is worth pausing to register how strange this result is. A region inside the black hole, behind the event horizon, causally disconnected from the outside universe by every classical measure, is nevertheless quantum mechanically entangled with the radiation that escaped. Your intuition says the interior and the exterior are completely separate. The island formula says they are not. Somewhere in the deep structure of quantum gravity, the wall between inside and outside is not as solid as general relativity led us to believe. This result does not fully resolve the information paradox. It shows that the page curve can be derived, that unitarity is consistent with the gravitational calculation, and that something like islands must exist if the framework is correct. But it does not tell us at a microscopic level how the information physically gets from the interior into the radiation. It does not explain what an infalling observer would experience. And it raises a new question, one that erupted 7 years before the island papers were written, in a sharp and startling argument about what an astronaut would encounter at the event horizon of an old black hole. In the summer of 2012, 4 physicists at the University of California, Santa Barbara, published a paper that detonated a quiet bomb in the foundations of black hole physics. Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, known collectively by their initials, AMPS, presented an argument so clean and so uncomfortable that it divided the theoretical physics community almost overnight. The argument went like this. Consider a black hole that has been evaporating for a long time, past the page time, past the halfway point, into the regime where, if unitarity holds, the Hawking radiation must be purifying itself. Each newly emitted photon must be entangled with the radiation already out there, because that is what the page curve requires. The new photon and the old radiation share quantum correlations. But Hawking's original calculation also requires something. Each outgoing photon is produced in a pair, one escaping, one falling inward past the horizon. For the event horizon to remain smooth, for a falling observer to notice nothing unusual as they cross it, the outgoing photon must be entangled with its ingoing partner. This is a requirement of the equivalence principle, the foundational postulate of general relativity that says a freely falling observer should experience locally flat space-time, with no dramatic effects at the horizon. Here is the trap. Quantum mechanics has a rule called monogamy of entanglement. A particle cannot be maximally entangled with two different systems simultaneously. If the outgoing photon is maximally entangled with the early radiation, as unitarity demands, then it cannot also be maximally entangled with its ingoing partner. And if the entanglement between the outgoing and ingoing photons is broken, the smooth vacuum state at the horizon is destroyed. What replaces it is a wall of high-energy radiation, a firewall, that would incinerate anything attempting to cross the event horizon. 3 pillars of physics and AMPS showed that they cannot all stand at once. Unitarity says information must be preserved. The equivalence principle says the horizon must be smooth. Monogamy of entanglement says a quantum system cannot be maximally correlated with two others simultaneously. Pick any two, and the third must fall. Polchinski, in subsequent interviews, described the situation with characteristic directness. The firewall argument was not a proposal, he said. It was a paradox, a proof that something we believed was wrong, without telling us which thing. And the candidates were all terrible. Give up unitarity, and quantum mechanics is broken. Give up the equivalence principle, and general relativity is broken. Give up monogamy of entanglement, and quantum information theory is broken. No comfortable exits. The response from the physics community was swift, diverse, and deeply divided. Some physicists accepted the firewall as the least bad option, a real physical phenomenon that fundamentally changes what happens at the event horizon of an old black hole. In this picture, the event horizon is not the invisible threshold we described in earlier chapters. For a black hole past its page time, crossing the horizon would not be a gentle, unnoticeable transition. It would be lethal. The falling observer would hit a curtain of Planck energy radiation and be destroyed before ever reaching the interior. Others pushed back. Daniel Harlow and Patrick Hayden argued that the computational complexity of extracting information from the early Hawking radiation might protect the horizon, that the operations required to verify the entanglement would take so long that by the time you finished, the black hole would have already evaporated. The firewall exists in principle, they suggested, but is computationally inaccessible. Nature hides behind complexity. And then there was the response that reshaped the entire conversation. In June of 2013, Juan Maldacena and Leonard Susskind, two physicists whose previous work had already transformed the field, published a paper with a deliberately understated title, Cool Horizons for Entangled Black Holes. The paper proposed a connection so unexpected that Susskind later said it hit him the moment he received Maldacena's cryptic email containing just 3 letters, an equals sign, and 3 more letters. ER equals EPR. The equation is not really an equation, it is a conjecture, a proposed identity between two of the most famous concepts in 20th century physics, both of which trace back to Albert Einstein, and both of which were published in 1935, the same year, at the Institute for Advanced Study in Princeton. ER refers to a paper by Einstein and Nathan Rosen describing what are now called Einstein-Rosen bridges, wormholes, connections through the interior of space-time linking two distant regions. In their simplest form, these bridges connect two black holes. They are not traversable. You cannot send a signal or a traveler through them. but they are real geometric structures within general relativity, shortcuts in the topology of spacetime that exist even though no one can use them. EPR refers to a paper by Einstein, Boris Podolsky, and Nathan Rosen describing quantum entanglement, the phenomenon in which two particles can share correlations so tight that measuring one instantly determines the state of the other, regardless of the distance between them. Einstein famously called this spooky action at a distance and considered it evidence that quantum mechanics was incomplete. For nearly 80 years, these two papers were treated as unrelated. Wormholes were a topic in general relativity. Entanglement was a topic in quantum mechanics. They belonged to different departments, different conferences, different vocabularies. Maldacena and Susskind proposed that they are the same thing. Every pair of entangled particles, they argued, is connected by a microscopic wormhole, an Einstein-Rosen bridge at the Planck scale. The bridge is far too small and far too quantum mechanical to allow any signal or information to pass through, which is why entanglement cannot be used for faster-than-light communication. But the connection is there, woven into the geometry of space-time at the deepest level. Entanglement does not just correlate distant particles, it builds the spatial connections between them. It stitches space-time together. Mark van Ramsdonk, a physicist at the University of British Columbia, had explored a closely related idea in a thought experiment published in 2010. He showed that in the ADS/CFT framework, if you took an entangled quantum state on the boundary and gradually reduced the entanglement between two halves, the corresponding spacetime in the bulk would pinch off and eventually disconnect. Remove the entanglement, and the spatial connection between the two regions vanishes. Spacetime does not exist independently of quantum entanglement. It is, in some fundamental sense, made of it. If ER equals EPR is correct, it offers a way out of the firewall paradox. The entanglement between the outgoing Hawking photon and the early radiation is not a separate, competing link that violates monogamy. It is the same connection as the one between the outgoing and ingoing photons, viewed from a different angle, a wormhole that links the radiation, already far from the black hole, to the interior behind the horizon. The two entanglements that AMPS showed could not coexist are, in this picture, the same entanglement described in two different languages. There is no conflict because there is no doubling. The horizon remains smooth, the information is preserved, and the price is a radical revision of what space-time is, not a fixed stage on which quantum events play out, but a structure that emerges from those events, knitted together by the invisible threads of entanglement. Is ER equals EPR correct? No one knows. It remains a conjecture, compelling, beautiful, supported by calculations in specific settings, but unproven in general. Almairi himself, when asked in 2017 where the field stood, answered with a candor that is rare in theoretical physics. "I would say we are still confused," he said. "There is no completely satisfactory resolution. It might mean that we are not asking the right question, and we do not know what the question is." That honesty matters. The firewall paradox has not been solved. It has been illuminated from several angles, by islands, by ER equals EPR, by the page curve calculations, and each angle reveals part of the picture without completing it. What is becoming clear, even through the confusion, is that the relationship between the interior and exterior of a black hole is far stranger than anyone imagined. That information, entanglement, and the geometry of space-time are bound together in ways our current theories can only dimly perceive. And one of the strangest implications of that entanglement, the idea that launched 1,000 subsequent papers, is the possibility that the entire three-dimensional universe we inhabit might be a projection, a shadow, a hologram encoded on a distant two-dimensional surface. The idea begins with a question about entropy that should not have led where it did. In 1972, Jacob Bekenstein, a graduate student at Princeton working under the supervision of John Wheeler, was thinking about what happens when you drop something hot into a black hole. A cup of tea, say, or a box of gas. These objects carry entropy, a measure of the disorder in their internal states, the number of microscopic configurations consistent with their macroscopic appearance. The second law of thermodynamics says that the total entropy of a closed system never decreases. It can increase or stay the same, but it cannot go down. This is one of the most robust laws in all of physics. It has never been violated in any experiment, in any context, at any scale. But a black hole seems to violate it trivially. Drop the tea into the black hole. The tea crosses the event horizon and disappears. Its entropy, the disorder it carried, vanishes from the observable universe. The total entropy of the region outside the black hole has decreased, and nothing has visibly increased to compensate. The second law appears to be broken. Bekenstein's insight was simple and radical. He proposed that black holes themselves carry entropy, and that this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. When the tea falls in, the black hole's mass increases, its horizon area grows, and the entropy associated with that area increases by at least as much as the entropy the tea carried. The second law is saved, but only if you count the black hole's horizon as a repository of entropy, a ledger where the universe keeps its accounts. At first, this was a conjecture, motivated by thermodynamic reasoning, but lacking a precise numerical coefficient. Bekenstein could say that entropy was proportional to area, but he could not pin down the constant of proportionality. That constant was fixed 2 years later, when Hawking's calculation of black hole radiation revealed the temperature of a black hole, and the first law of thermodynamics, the relationship between heat, temperature, and entropy, did the rest. The result is the Bekenstein-Hawking entropy formula. The entropy of a black hole equals 1/4 of the event horizon area, measured in Planck units. 1/4, not 1/2, not 1, not pi, 1/4, a number that drops out of the mathematics with no room for negotiation. Take a moment to consider how strange this is. In every other physical system we know of, entropy scales with volume. A box of gas has twice the entropy of a box half its size, all else being equal. The number of ways molecules can arrange themselves grows with the space available to them. This is so intuitive, it barely seems worth stating. More room, more configurations, more entropy. A black hole breaks this pattern. Its entropy is determined not by the volume enclosed within the horizon, but by the area of the horizon itself. A black hole with 10 times the radius does not have 1,000 times the entropy, as it would if entropy scaled with volume, but only 100 times, because the area scales as the square of the radius. The information content of a black hole lives on its surface, not in its interior. Bekenstein himself recognized the strangeness of this result, but it took 2 more decades for its full implications to crystallize. In the early 1990s, Gerard 't Hooft, a Dutch Nobel laureate in physics, and Leonard Susskind independently pursued an idea that grew directly from the area-entropy relationship. If the maximum entropy that can fit inside a region of space is determined by the area of the region's boundary, and if entropy is a measure of information, then the maximum amount of information that can exist inside any volume of space is encoded on the surface that encloses it. This is the holographic principle. It states that the physics of a 3-dimensional region can be fully described by information living on its 2-dimensional boundary, not a summary, not an approximation, a complete description. Every particle, every interaction, every quantum state, everything happening inside the volume is, in principle, encoded on the surface surrounding it. at a density of at most 1 bit per Planck area, 1 bit per 4 Planck lengths squared. The grainiest, most fundamental resolution at which information can be inscribed on a surface. Susskind, never one to understate a result, put it this way: the three-dimensional world of ordinary experience, the universe of galaxies, stars, planets, and people, is a hologram, an image of reality coded on a distant two-dimensional surface. If this sounds impossible, or at the very least wildly speculative, consider that it has a concrete realization, one that has been studied, tested, extended, and confirmed in hundreds of independent calculations over nearly 3 decades. That realization is the ADS/CFT correspondence we encountered in the previous chapter. In the ADS/CFT framework, the holographic principle is not a metaphor. It is a precise mathematical statement. The gravitational physics of the bulk, the interior of the anti-de Sitter spacetime, complete with black holes, gravitational waves, and curved geometry, is entirely captured by a quantum field theory on the boundary, 1 dimension lower, with no gravity at all. The boundary theory is the hologram. The bulk is the projected image, and the two contain identical information. This framework made it possible in 1996 for Andrew Strominger and Kamran Vafa to accomplish something that had eluded physicists for 2 decades: a microscopic accounting of black hole entropy. Using string theory, they constructed a specific type of black hole and counted, one by one, the quantum microstates that correspond to it, the individual configurations of strings and branes that produce a black hole with a given mass, charge, and spin. The number they found matched the Bekenstein-Hawking formula exactly, not roughly, not to within a factor of 2, exactly, including the factor of 1/4. This was not a derivation of the holographic principle from first principles. It was a consistency check, a demonstration that, within the framework of string theory, the area-entropy relationship has a microscopic explanation. The entropy is real. The microstates exist. The surface really does encode the interior. Since then, the holographic principle has permeated nearly every corner of theoretical physics. It underlies the island formula. It motivates the ER equals EPR conjecture. It provides the framework within which the page curve was derived. And a newer branch of research, celestial holography, developed by Andrew Strominger and collaborators beginning around 2016, is attempting to extend holographic ideas beyond anti-de Sitter space to the flat space-times that more closely resemble our actual universe, potentially making the principle testable through gravitational wave observations with instruments like LIGO and the future space-based detector LISA. There is something vertiginous about the holographic principle. It says that depth, the dimension that gives the world its apparent thickness, that separates your chest from your back, that allows you to walk into a room rather than merely across a painting, might not be fundamental. It might be emergent, arising from patterns of information on a boundary you cannot see, at a distance you cannot measure, in a way that our current mathematics can describe but our intuition cannot absorb. Whether the holographic principle applies to the entire universe, or only to regions bounded by horizons, or only to spacetimes with negative cosmological constants, is not settled. What is settled is that the entropy of a black hole is written on its surface. And any theory that claims to explain what happens inside a black hole, at the singularity, behind the horizon, in the deep interior, must ultimately be compatible with that fact. Several such theories have been proposed. Each offers a different answer to the question of what replaces the singularity. Each makes predictions that differ, sometimes subtly, sometimes dramatically. And for the first time in the history of black hole physics, some of those predictions may be within reach of observation. We have arrived at the frontier. Everything we have discussed so far, the event horizon, the singularity, Hawking radiation, the information paradox, the firewall debate, the holographic principle converges on a single unsolved problem. What actually replaces the singularity at the center of a black hole? General relativity predicts a point of infinite density. Quantum mechanics says that infinite densities cannot exist. Something must give. Something must replace the classical picture with a quantum one. But since no complete theory of quantum gravity exists, the best physicists can do is propose candidates. Models that attempt to describe the deep interior using the partial tools available. Each one offers a different vision of what lies at the center. Each one makes predictions that, in some cases, may eventually be tested. 3 proposals, in particular, have shaped the last 2 decades of research. The first comes from string theory, and it is called the fuzzball. In 2001, Samir Mathur, a physicist at Ohio State University, published the first in a series of papers that radically reimagined the interior of a black hole. In the standard picture, a black hole consists of an event horizon surrounding empty space, with a singularity at the center. In Mathur's picture, there is no empty interior, and there is no singularity. The entire region inside what we would call the event horizon is filled with a dense, tangled structure made of strings, the one-dimensional objects that string theory posits as the fundamental constituents of matter and energy. These strings vibrate in complex patterns, interweaving in higher dimensions, forming an object Mathur called a fuzzball. The name is deliberate. A classical black hole has a smooth, featureless horizon, no texture, no structure, nothing to distinguish one point on the horizon from another. A fuzzball has texture. Its surface is fuzzy, irregular, structured at the Planck scale. There is no horizon in the traditional sense, no sharp boundary between interior and exterior, and no singularity at the center, because the strings provide a physical structure that fills the volume and prevents the collapse from reaching infinite density. The remarkable thing about fuzzballs is that their size matches. Mathur's calculations show that the radius of a fuzzball for a given mass corresponds precisely to the Schwarzschild radius predicted by general relativity. From the outside, at a distance, a fuzzball would be virtually indistinguishable from a classical black hole. It would have the same mass, the same gravitational pull, the same shadow if imaged by a telescope. The difference is entirely internal, but that internal difference resolves both the singularity and the information paradox in one stroke. Since the fuzzball has structure, since it is made of distinguishable microstates, each configuration of strings representing a different internal arrangement, the information about what fell in is encoded in the structure of the fuzzball itself. When it radiates, it does not produce featureless thermal radiation. It radiates from its surface, the way any hot object does, and the radiation carries information. In 2021, a team of Italian physicists ran computer simulations suggesting that the differences between a fuzzball and a classical black hole might be detectable in gravitational wave signals, specifically in the ring-down phase after 2 black holes merge. Classical black holes settle into a smooth final state. Fuzzballs, being extended objects with internal structure, would ring differently, with subtle echoes and modified decay rates that next-generation detectors like the planned LISA observatory might be sensitive enough to measure. No such echoes have been observed, but the search is underway, and the instruments are improving. The second proposal comes from loop quantum gravity, an approach to quantum gravity that does not rely on strings or extra dimensions, but instead quantizes space-time itself, treating the fabric of space as a discrete structure, woven from finite loops rather than continuous curves. In 2014, Carlo Rovelli and Francesca Vidotto proposed that the interior of a black hole might contain what they called a Planck star. The idea draws on a result from loop quantum cosmology. the application of loop quantum gravity to the early universe, which suggests that when matter is compressed to the Planck density, roughly 10 to the 93 grams per cubic centimeter, quantum gravitational effects generate a repulsive force that halts the collapse. This is not an ordinary force. It arises from the uncertainty principle applied to the geometry of space-time itself. Space cannot be compressed below a certain granularity, and the resistance to further compression acts as a kind of quantum pressure that prevents the formation of a singularity. In Rovelli and Vidotto's model, a collapsing star does not fall all the way to a point. It compresses to an extraordinary but finite density, forming a Planck star with a radius of roughly 10 to the minus 12 meters for a stellar mass black hole, far smaller than an atom but far larger than the zero-dimensional point that general relativity predicts. The collapse halts, and then, on an extremely long timescale, the Planck star bounces, expanding back outward in what would appear from the outside as a white hole, a time-reversed black hole that expels matter and radiation rather than swallowing it. The catch is time. Due to the extreme gravitational time dilation near the Planck star, the bounce that takes a fraction of a second in the star's own reference frame would take an extraordinarily long time as measured by an outside observer, potentially comparable to the evaporation time of the black hole itself. The Planck star is not trapped forever, but it is trapped for eons. The third proposal is less a specific model and more a general mechanism, and it emerged in 2020 from the work of Giordani and colleagues. They observed that any quantum system with a maximum entropy, including a black hole, experiences a back reaction as it radiates. The information stored in the black hole is carried by what they called memory modes, quantum degrees of freedom that are nearly gapless, meaning they require almost no energy to excite, which is what allows the black hole to store so much information in the first place. As the black hole radiates and loses mass, each emitted quantum leaves a cumulative imprint on these memory modes, gradually increasing the energy gaps between them. By the time the black hole has lost roughly half its original mass, the page time, the back reaction has become so strong that the semi-classical description of Hawking radiation breaks down entirely. The evaporation does not continue at its predicted rate. It slows dramatically, burdened by the memory of everything it has already emitted. This memory burden effect is not specific to black holes. It is a universal property of quantum systems at maximum entropy. But for black holes, it has a striking consequence. The standard prediction that a black hole of a given mass evaporates in a calculable time may be wrong. The late stages of evaporation could be far slower than Hawking's original estimate, potentially opening new mass windows for primordial black holes, tiny black holes formed in the early universe, to survive to the present day and contribute to dark matter. 3 proposals, 3 visions of what replaces the singularity, what lives inside the horizon, what happens at the end of a black hole's life. Fuzzballs built of strings, with structure where classical physics predicted emptiness. Planck stars held up by the quantum fabric of space, bouncing on timescales that dwarf the age of the cosmos. Memory-burdened remnants, slowed to a crawl by the weight of their own radiated history. None of these is proven. None is universally accepted. Each has strengths. Fuzzballs naturally resolve the information paradox. Planck stars naturally resolve the singularity. The memory burden effect naturally explains why semi-classical calculations might break down at the page time. Each has weaknesses. Fuzzballs require the full machinery of string theory to be correct. Planck stars rely on extrapolations from loop quantum cosmology that have not been rigorously derived in the full theory, and the memory burden mechanism does not specify the microscopic physics of the interior. But what is new, genuinely, historically new, is that some of these ideas may be testable. We are no longer limited to pen and paper. We have gravitational wave observatories that have detected over 300 black hole mergers. We have radio telescope arrays that have photographed 2 event horizons. We have instruments being designed right now that will see further, hear more clearly, and measure more precisely than anything that has come before. And that brings us to the final chapter of this journey. Not a conclusion, but a pause at the edge of what we know, looking outward into what we might one day understand. On the 14th of September 2015, at 5:51 in the morning Eastern Daylight Time, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, one in Livingston, Louisiana, the other in Hanford, Washington, simultaneously registered a signal that had been traveling toward Earth for 1.3 billion years. The signal lasted less than 0.2 of a second. It swept upward in frequency from 35 Hz to about 250 Hz in a characteristic chirp that matched with extraordinary precision the predictions of general relativity for 2 black holes spiraling into each other and merging. The black holes were roughly 36 and 29 times the mass of the Sun. The final object was 62 solar masses. The missing 3 solar masses, about 6 trillion kilograms, had been converted entirely into gravitational wave energy, radiated outward as ripples in the fabric of space-time. The detection required measuring a change in the length of each 4-kilometer detector arm of less than 1/10,000th the diameter of a proton. That was GW 150914, the first direct detection of gravitational waves and the first direct observation of a black hole merger. It confirmed a prediction Einstein had made 99 years earlier and opened a window onto the universe that had been closed for the entire history of astronomy. We had always observed the cosmos through light. Now, for the first time, we could listen. In the decade since that first detection, the window has swung wide open. The LIGO-Virgo-Cagra collaboration, a global network of detectors spanning the United States, Italy and Japan, has observed over 300 black hole mergers. In March of 2026, the collaboration released its 4th gravitational wave transient catalogue, containing 128 new events detected during a 9-month observing period alone. Black hole mergers, once theoretical curiosities, turned out to be common. The universe is full of dead stars colliding in the dark, shaking space-time as they fall into each other, broadcasting their final moments in a language that only became audible to us a decade ago. Among those detections, 2 stand out. In January of 2025, LIGO recorded an event designated GW 250114, a merger of 2 black holes, each about 33 solar masses, 1.3 billion light-years away. The signal itself was not unusual. What was unusual was its clarity. The signal-to-noise ratio reached 80, more than 3 times cleaner than the first detection a decade earlier and the highest ever recorded. That clarity made it possible, for the first time, to isolate and measure the gravitational wave overtones emitted during the ring-down phase. The brief period after the merger, when the newly formed black hole vibrates like a struck bell, shedding its asymmetries and settling into a stable Kerr geometry. 2 distinct tones were identified in the signal, and from their pitch and decay, physicists extracted the mass and spin of the final black hole with unprecedented precision. The results confirmed the Kerr solution, Einstein's description of a rotating black hole, and provided the strongest observational evidence to date for Hawking's area theorem, the principle that the total event horizon area of the merged black hole must be at least as large as the sum of the original 2. Hawking published the area theorem in 1971. 54 years later, LIGO heard it ring true. 7 months after that, in July of 2025, the collaboration announced the detection of GW 231123, the most massive binary black hole merger ever observed. 2 black holes, approximately 100 and 140 solar masses respectively, spiraling together to form a single object of 225 solar masses. Both components were spinning near the maximum rate allowed by general relativity. Their masses placed them squarely in a range that current astrophysical models struggle to explain, the so-called pair instability gap, where the physics of stellar evolution predicts that black holes should not form. The detection challenges assumptions about how massive black holes come to exist and hints that some may be second-generation objects. Black holes formed not from collapsing stars, but from the mergers of earlier, lighter black holes, compounding their mass through successive collisions over cosmic time. Meanwhile, the Event Horizon Telescope has continued its own campaign. After the historic images of M87 star in 2019 and Sagittarius A star in 2022, the EHT collaboration used data from its 2021 observing run to probe deeper into the environment of M87 star. In January of 2026, researchers published a study identifying, for the first time, the base of the relativistic jet, the column of charged particles launched from near the black hole at nearly the speed of light, extending over 3,000 light-years into intergalactic space. By combining observations at different baseline lengths, the team was able to trace the jet back to a compact emission region just outside the glowing ring of the original image, connecting the shadow of the black hole to the origin of one of the most powerful, sustained energy outputs in the known universe. The next generation Event Horizon Telescope, the NGEHT, is already under construction. It will double the number of radio dishes in the global array, observe at new frequencies, and for the first time produce not still images but movies of black holes, capturing the motion of hot gas orbiting the event horizon in real time, frame by frame, shadow by shadow. Within the next decade, we may watch a black hole eat. Let us pause here for a moment. Not because the science is finished, it is nowhere close to finished, but because we have traveled a long way tonight, and it is worth looking back at the road. We began with a clock falling towards something it could not see. We followed that clock through the death of a star and the birth of a black hole, past the event horizon and into the interior, through spaghettification and time dilation and the breakdown of geometry itself. We encountered a radiation that should not exist, a paradox that split physics down the middle, and a set of proposals, islands, firewalls, wormholes, holograms, that suggest the architecture of reality is far stranger and far more deeply interconnected than anything our everyday experience would lead us to expect. And at the center of it all, there is still a question mark. The singularity, or whatever replaces it, remains hidden. Not because we lack curiosity or ambition or instruments, but because the answer, when it comes, will require a new understanding of what space and time actually are. Not the smooth, continuous fabric Einstein described, not the fixed, absolute stage Newton assumed. Something else. Something that emerges from quantum entanglement or dissolves into it. Something we have not yet learned to say. There is a particular quality of wonder that belongs to the things we do not understand. It is different from the satisfaction of a solved problem or the elegance of a proven theorem. It is quieter than that, more persistent. It is the wonder of standing at the edge of a map and knowing that the territory continues, that the blankness is not emptiness, but uncharted ground. Kara deliklerin karanlur, the darkness of black holes, is that kind of blankness. It is not the darkness of ignorance. It is the darkness of a question so fundamental that answering it may reshape every other answer we have. What is space-time made of? Can information survive the most extreme gravitational compression the universe allows? Is the three-dimensional world we walk through a projection from a surface we can never touch? These questions were not available to us a century ago. They became possible only because a teenager on a ship calculated a limit, because a soldier in a trench solved an equation, because a physicist in a wheelchair imagined radiation emerging from nothing, because 1,000 engineers built mirrors so sensitive they could measure a distance smaller than an atomic nucleus. Each step was improbable. Each step required someone to look at the darkness and see not an ending, but a doorway. The universe has been here for 13.8 billion years. For almost all of that time, it contained no one capable of asking what a black hole is. No one to notice that time bends near heavy objects, or that information might be written on surfaces rather than volumes, or that space-time might be stitched together by entanglement so subtle it took 80 years to recognize. And now there is someone. Billions of someones on a small planet orbiting an ordinary star in the outer arm of a spiral galaxy that itself orbits a supermassive black hole. One of the very objects we have spent these hours trying to understand. The fact that we can ask these questions, that we arose from the debris of dead stars and developed a language precise enough to interrogate the fabric of reality, is not a footnote in the story of the cosmos. It may be the most remarkable thing the cosmos has produced, not because we are large or powerful or permanent, but because we are the mechanism by which the universe examines itself. The instrument turned inward, the darkness becoming aware of its own depth. We do not yet know what lies at the center of a black hole. We may not know in our lifetimes, but the asking is not wasted. Every question, every instrument, every equation that fails, each one maps another inch of the territory beyond the edge of the known. And the territory is vast, and the night is long, and there is nowhere you need to be. The stars outside your window, some of them are already dead. Their light is still arriving, crossing the void at 300,000 kilometers per second, carrying the image of something that no longer exists. That is what starlight is. A message from the past traveling through the present, reaching a consciousness that will one day be part of the past itself. Let the questions rest for now. They will still be there in the morning at the edge of the map, waiting. The darkness does not mind being patient. It has been patient for a very long time. Rest now. Let the cosmos hold you. Sleep well. Good night.